So today's speaker is Stefan Hegselmann. He will talk about, you can see it on the slide here, interpretable machine learning in healthcare. So a really timely and very, very exciting topic. You know, everyone is very interested in AI. And so recently I read that one of the key problems in bioinformatics, for instance, was now solved or almost solved by AI technology. When I came into this field, say 25 years ago, there was a lot of work about bioinformatic simulations of protein shapes from amino acids. And so recently, an AI software was published and in a challenge demonstrated that it outperforms all other methods and is very close to experimental validations, which are very time consuming. So it's really a timely topic. And Stefan did a lot of work in this field, not in the bioinformatics field, but more how you can use AI technique to work with clinical data. And so, Stefan, we are very much looking forward to your presentation. The floor is yours.
Yeah, thank you very much for the kind introduction. My name is Stefan Hegselmann. Welcome to today's seminar about new methods in medical informatics. And as Professor Lugas already said, I want to talk about interpretable machine learning in healthcare. And this is a rather broad topic, so it's probably quite difficult to cover that in a single talk. No less, I will try to both give you an overview about existing literature and also just adjust the windows a little bit here. An overview about existing literature, but also an insight into the work that I'm doing. And to this end, I split up the talk into three parts. The first one, which will roughly take half of the time, will be the literature review that I mentioned, or this overview about interpretable machine learning with a slight focus on healthcare. And the second part, first I will give you some background and motivation for that, and then I will present to you some finished work that was done together with the Department of Anesthesiology here at the University Hospital, which is an evaluation of interpretability of a machine learning algorithm. And the last part will be some preliminary results of an ongoing project, also joint work with the Department of Anesthesiology, where we actually used this model that we evaluated for its interpretability here in part 2 for a 7-day intensive care unit readmission prediction. Okay, but let's start out with a motivational example. So why would interpretability be necessary for machine learning? And this is kind of a prime example for interpretability. It's from a paper by Rich Caruana et al., where they train a so-called generalized additive model with interaction, abbreviated as GAM, which I will now use as a term for these models, to predict the probability of death for pneumonia. Pneumonia is an infectious disease of the lung, which can cause serious troubles for the patients. And these kind of models, during training, you get these so-called risk functions for single variables. So you can see, for instance, for age, you have all the variable values on the x-axis and the associated risk on the y-axis. The same for cancer. And you also, this is what this for with interactions, and the name of the model stands for pairs of variables. You get visualized as a heat map the risk of combinations of these variables. Exactly. So, and then this is what you get from training. And when you now have a new incoming patient or whatever new instance you want to predict, you just look up into your you go into risk functions, look up the associated values. So, for instance, here for age, for 90, you would pick up the risk value. The same for cancer and also in these heat maps. And you just sum up these risk scores, and then you will get the log odds for the predicted label. And the log odds is just a transform probability. And it's interpreted as follows: 0 would be average risk, negative values are lower than average risk, and the positive risk score are higher than average risk. And they trained these models for the specific task of probability of death for pneumonia, to do risk stratification for patients, and to target like patients at risk. And here are just some of their trained risk functions, and you can see for age, for instance, here these green bars are just confidence intervals, which kind of include the function a little bit, so don't be confused by those. That for an age, I would say until 70, You have lower than average risk, and after that you have an increased risk, which is like the highest for age around 90. For cancer, which is a binary variable, so if you have a condition of cancer, if you have cancer, you have an increased risk, otherwise you have average risk. And then these heat maps, which are obviously a little more difficult to interpret. You have age on the y-axis, cancer on the x-axis. And then you can see from this one, for example, that if you're a younger patient, so age around 20, you have a condition of cancer, you are at an increased risk for death for pneumonia. So this is basically how these models work and how you can try to interpret them. And here on the right, you see one particular risk function that is also highlighted in the paper. It is the risk function for the condition of asthma. And you can see that people don't have asthma, they have average risk. But if they have a condition of asthma, they actually have decreased risk. So the model learned that asthma lowers the risk of dying from pneumonia, which is clearly against medical evidence. And so if you would now deploy such a model in an emergency department to do risk stratification, you would actually do like a systematic error that you systematically underrate the probability of death for pneumonia patient that have a condition of asthma, which is of course like a serious problem. Yes, and this is of course like a common pitfall that can happen if you do machine learning with data that was not controlled in a controlled environment, as it would be in like a statistic for statistics. And just one more note about this slide. Also, the authors were kind of surprised by this result because they worked extensively with this data and also trained a bunch of other models on it. But this association of data never really occurred to them. So it really, they really needed to train this, as they call, transparent model, and to really pick up this correlation in the data. And then they went back and looked at the previously trained model, and they actually also picked up this correlation. So they had it, they also had it in their predictions, but it occurred to no one. And this made kind of these authors like very strong advocates of training such transparent models for mission critical decisions. Okay, so that's the motivational example. And just to show you that this is not like an isolated problem in machine learning, I guess most of you already know some of these problems. Just put on these kind of loose categories here to give you some more examples. The first one would be overly relying on correlations. On the right, you can see an example of an analysis of the Google Flu Trends prediction system. So the authors, that's a system by Google that attempts to predict the size of the outbreak of the yearly flu from Google search queries. The authors found that in the beginning, so this is not displayed here in this graph, actually this tool picked up a lot of search terms that were just predicting winter. And after Google removed those, this tool completely missed one flu season because the flu is usually coming out in January. So it helps you to have like an indicator when the season starts. But after removing those, the tool completely failed. So you saw it picked up some wrong correlations. Also, this overshoot here, so this orange one is the Google flu prediction, is simply due to a change in the suggestion algorithm of Google. So it also, you could say, these were wrong correlations that the tool picked up. The second problem are bias predictions. This is an example of an analysis of a very popular tool called Word2Vec, which gives you vector representations of words. So word embeddings, which are very popular in the NLP community. And if you have these vector representations of words, you can actually do mathematical operations for them, which is quite nice. So you pose questions like, man relates to a woman as a king too, and then as an answer you would get queen, because this is the word that kind of fulfills this approximation the best. But you could also ask questions, man relates to a woman like a computer programmer too, and as an answer you would get homemaker, where you can see that kind of the system picked up biases and past data. And if you would now use such a tool, you would of course reinforce like stereotypes from the past, which can be problematic. And the last one would be missing robustness. So that's an example where you have a neural network to recognize pictures. On the left side, this picture is correctly classified as a dog. And after applying some slight perturbations to this picture, which are not really visible to the human eye, it is misclassified as a bird. So that can also cause problems. There are certainly some more problems that can occur, but that just as an overview. Okay, so where does interpretability step in now? As Loshivele said, I'll put it, the need for interpretability stems from an incompleteness in the problem formalization. Okay, so what does that mean exactly? Usually during machine learning training, we optimize some kind of loss function that we define, and we want to minimize it usually. But the problem is that we can't put all properties that we maybe want from a machine learning system into such a loss function. If, for instance, you consider fairness, if we sit together in a group and discuss what fairness means to us, that's probably quite hard already. But if we now have to come up with a mathematical formalization of this property, it would probably be impossible. And the idea of interpretability now is to allow humans like an insight into the model, or humans hopefully that they understand the model, at least to a certain extent, so that they could ensure that some properties such as fairness are met by the system. So interpretability allows to put the responsibility for additional properties such as fairness or unbiasedness on humans. And I really like this idea because I really think that there are some properties that you can't really encode in a mathematical formula. And it's kind of a nice idea to move this like from math to humans deciding what's fair for us. Then you could ask if you need interpretability like in all instances, and certainly not. So when you just have an app classifying dogs and cats, it won't be that relevant for you. So the authors say, it's especially useful when you have significant consequences of your predictions. And secondly, there's not enough empirical evidence that your system works correctly. And that kind of also shows already like a different avenue that you can take instead of interpretability. So that's only one possibility that you can use. You could also do like extensive empirical evaluation of your tools to ensure, for instance, safety. You could also do experiments to ensure fairness, for instance. So you don't necessarily need interpretability techniques. Yes. And this first point, that we have significant consequences of our predictions, we actually find quite often in healthcare, which is why interpretability might be a useful technique there. However, it can be a little bit tricky to determine if you need it or not. On the right here, you see a picture that was taken from a publication, Interpretable Machine Learning in Healthcare, where they state that there are like different levels of predictions where you might need interpretability in healthcare. So for instance, they say for decisions at end of life, you probably need a high level to ensure high safety because these are very critical decisions. On the other hand, they say cost predictions, for instance, are not that important. And I mean, it is kind of intuitive to say that. The problem is you could also get problems at the lower end here. And just to illustrate that, down here, I mentioned a study by Obermeyer et al., who analyzed a system in the US that is meant to predict future healthcare needs. They use the system to target people who will probably need healthcare service in the future, and they call them or send them letters to offer them a medical checkup. The problem is that there is no label you could use from the past which shows you healthcare need. So what they did instead was to use the healthcare spending as a proxy label, so which is something like the costs. And as it played out, like the wealth in the US is not evenly distributed. And this tool showed a racial bias in predicting who needs healthcare. And what is really interesting is that this tool was used for millions of people and had this strong racial bias in it, which I think is very impressive work. And the second factor why interpretability could be useful, because it can help to build trust and decrease uncertainty with the stakeholders if you plan to really deploy a machine learning system. Because that's often a problem, that machine learning systems are developed and like the developers are really convinced by it. But then if you want to translate it to clinical care, there are a lot of barriers for doing this deployments. And interpretability could help out there. Okay, so now we've seen some problems with machine learning and like instances where, or like how interpretability could help us there. And now I just briefly want to talk about how to evaluate interpretability and what it really means to have an interpretable machine learning system. And that's really a hairy subject, I would say. It's quite tough. because the problem is that interpretability is highly context specific. So what does that mean? That's actually a paper Professor Lucas pointed out to me, which describes this problem quite nicely. It is from the healthcare perspective and looks at different viewpoints of this concept from a technological, legal, medical, and patient perspective. And you see that, like, depending on which viewpoint you take, and there might be very different desiderata for interpretability. For instance, from a technological perspective, as a developer, you might want to use these techniques as a sanity check, and that's enough for you. From a legal perspective, on the other hand, you want to comply with existing law, like the GDPR. There you have a right for explanation, so you really want to have a good enough explanation to adhere to this existing law. And it also depends a lot on the people you want to make the system interpretable for. So if you ask us, for instance, as a text-heavy audience, probably we would be fine with interpreting a logistic regression function of a standard deviation feature. But if you design a system for like patients to explain their diagnoses, that could cause problems because not everybody knows how to interpret a standard deviation, and they're also not familiar with a logit function. Yeah. So the questions you really have to ask is, make the system interpretable for whom, for what task, and to which ends. And in the machine learning community, I think there's consent now that if you really want to show this for your system, you have to do evaluations with real human beings. So this is a taxonomy introduced in this work, taxonomy of evaluation approaches for interpretability. And you see here at the top, kind of the gold standard would be application ground evaluation with real human beings. In the best case, really your target population and the real task at hand. And so then really you have to test the system without your interpretability tools. And with your interpretability tools, you really have to see if adding interpretability really improves the outcome that you want to tackle. So for instance, if you want to spot biases in your predictions, you have to check if adding this interpretability component helps people to spot biases in the predictions. So actually, I would say it's very similar to what we do in usability studies. So there you also have to work with real human beings and use their feedback to determine if the system is usable in a nice way. And I think this is something that is often a little bit underrepresented in publications that claim interpretability of their systems. They don't really have made such studies because it's, of course, a large effort to do that. But yeah, actually that would be necessary to make these claims, or at least discuss that these experiments were not feasible, and discuss that maybe the system is not that interpretable as the authors might think. Okay. Now I want to come to like concrete methods, how you could ensure interpretability for your machine learning system. And here it is important that we distinguish two classes of methods. And the first one would be so-called transparent models, sometimes also called glass box. Here the idea is to build a rather simple model that hopefully human beings can understand and make sense of. There are like some standard methods, I guess most of us know, like linear logistic regression or decision trees. And also, which is sometimes a little bit underappreciated with all these new developments with neural networks, that there are also new algorithms in this field, like these GAMs that I've shown in the motivational example, but also falling rule lists or two-layer additive risk models. So there are a lot of new developments in this field also. But there's something very important that you have to understand, kind of a warning. There are no inherently interpretable models. So you can't say we use decision tree, so we have an interpretable model. If you look, for instance, at the picture on the right side, it's very small, I know, but it's just about the idea. It's a very complex decision tree. And if I now would ask you if it's interpretable, it's not that clear because it's very complex. The same for a linear regression. If I show you a linear regression for 10,000 of features, it also won't be interpretable. Another problem can be highly engineered features. So if you have like the mean of the blood pressure to the power of 3, you would not really know, at least I wouldn't know how to make sense of that. So it really, keep that in mind. It does not only depend on the model, so transparent models help you to build interpretable models, but it also depends like how you apply them. Yeah, and in the end, you have to make this evaluation I've just mentioned to check if they are interpretable for your use case. The second class, so-called Postdoc interpretability methods or black box models, where the idea is to build a complex model that probably no one can understand because it's too complex, but at least you have explanations for your predictions. Maybe just for the naming, sometimes people use the term explainable AI. Sometimes they refer to this second class of techniques. Sometimes they mean interpretability with as a synonym for interpretability. So yeah, that's sometimes a little bit difficult to distinguish. But that's the idea of the second class, post-hoc interpretability. And there were like a lot of new techniques developed recently because it's kind of appealing because they're often model agnostic. So you can use whatever model you want to use and add these explanation methods to your existing methods. But here also a warning. There are no simple explanations that can fully explain a complex model. That kind of sounds a little bit philosophical. Yeah, so the idea is if there would be simple explanations, you could simply use these simple explanations as your model and throw away the complex model. And usually that doesn't work out. So what you really have to understand is these simple explanations are just give you an idea of what's going on, but they can't possibly cover like all the complexity of the model. And to give you an example for this, consider the picture on the right side. Here we see a so-called saliency map, which highlights which pixels are important for your network to predict a certain label. And the example on the left is, and these saliency maps are often used as explanations. And on the left, you can see a saliency map for this picture being a Siberian husky, which might be right. And on the right, you see a saliency map for this picture being a transverse flute. So yeah, at least I don't learn a lot from the explanation on the right side. It doesn't really explain to me how the model is working. On the left, I can say, okay, it looks correct. I mean, the model somehow highlights the dog, but that's really all you can take from it. Some people use like terming, it shows you where the model is looking, which I think is very confusing and you shouldn't use. So yeah, you should just be aware of these limitations of these explanations. And since I've showed you these GAM models in the beginning, which are from this class of transparent models, I now also want to show you two techniques from this second class, so these post-hoc interpretability methods. And these are two recent techniques that are very popular nowadays. The first one is called the LIME, and it stands for Local Interpretable Model Agnostic Explanation. And I think it's a very good example for these techniques because it shows the common approach of those. The idea is that it learns a simple model in the vicinity of an instance that you want to explain. And this is kind of depicted here in the picture on the right. It's from the original paper. So you have a model, which is this shown in this light red. So this is the decision boundary, which is probably very complex. So very hard to explain this to a human being. And now you want to explain why you predicted this highlighted red cross as a cross. And to this end, you look in the neighborhood and weight all instances, so there are crosses and circles, according to their distance to the instance you want to explain. So the instances that are closer are a little bit bigger, the ones further away are very small and are possibly irrelevant for you. And based on these weighted instances, you build a simpler, in this case, a linear model, which kind of resembles the decision boundary in this neighborhood. And here it works very well, of course, because it's from the original publication. So you can see that this decision boundary in this neighborhood is resembled very well by this linear model. And then you can just give the weights of this linear model as an explanation. So it's a little more complicated than that, but that's the basic idea. And the second one would be so-called SHAP values, standing for Shapley additive explanations. Those are based on a game theoretic approach of Shapley values. So Shapley values are something different than SHAP values, which can be a little bit confusing. And the general idea here is that you want to find out the influence of a feature. And to that end, you build so-called feature sets. So in this picture, we have the features age, gender, and job. And you build feature sets with all combinations of features. So we have the empty set here at the top, then sets with single features, with pairs of features, and all three features. And then if you want to find out the influence of age for a prediction, you add age to all sets where it's not present yet. So to the empty one, to the gender and job one, and to the gender and job one. And then you check what does adding age to these feature sets change for the final prediction. And this kind of gives you a measure what's the influence of this feature. So this is how these Shapley values intuitively work. These Shapley values are an approximation of this, because as you can expect, if you have more features than this, you have an exponential blow up of this graph. So you need an approximation here, but these still fulfill the so-called Shapley properties, which is very nice because they have like some theoretical results about these explanations. So for instance, there is a dummy property saying that if a feature has no effect for a prediction, it should receive a Shapley value, and so also a Shapley value of 0, which is quite nice. So you get like some theoretical results about the explanations that you could use. There's also a symmetry property saying if two features have the same influence on a prediction, they should also receive the same Shapley value. So yeah, you have some constraints for the explanations, which makes them a really appealing tool, and a lot of people are using them. Yes. So I think for these postdoc interpretability methods, it's important to keep in mind these limitations that they have. But even though there are simplifications, I still think they're very useful tools to give you like some insights about what the model is doing and why the prediction is as it is. Just as a side note for the research, the literature research I've done for this talk, I also found a paper tricking Lime and Shep. So this just shows you that these explanation methods, you will always have ways to circumvent those. Okay. And now I want to finish this first part with two perspectives on this whole complex of interpretable machine learning. The first one on the left is by Cynthia Rudin. It's a paper called "Stop Explaining Black Box Machine Learning Models for High-Stakes Decision and Use Interpretable Models Instead." And I think this title, it was published in Nature, and this title kind of resembles quite nice her opinion. So she really says for high-stakes decision in healthcare, for recidivism prediction in the prison system, or for loan prediction, we should really use interpretable models, and she means transparent models that we can fully understand, and no black box models with post-hoc explanation. She also states that she thinks it's a myth that there is an accuracy versus interpretability trade-off that is often cited. You can see it down here. So often you hear that you have to make a trade-off. Either you have a model that is performing very good, or you have a very interpretable model. One example here is from a Google paper where they use thousands of EHR records to do prediction with neural network. And actually in the supplement, you can see that logistic regression just performs as well as the neural net. So this is kind of some evidence against this trade-off. Still, I can say for some problem instances, you might have something like this, but for healthcare, I think it is quite hard to make such a statement that there is a trade-off. So I think I would agree with her. And she argues that usually it's just an issue of extra effort you have to take to build really interpretable models. So that's some impression of her work also. Her group often take on like existing black box models and with the mission to build an equally performing model that is transparent. On the right, you can see, like as a contrast, another example by Mark Sendak et al. It's called Sepsis Watch Real-World Integration of Deep Learning into Routine Clinical Care, which is an example where they translated a deep learning system into routine healthcare. And it's interesting because right from the beginning, they say we don't need any method, any interpretability method. We have other means to establish, for instance, trust or safety. Trust, they say they, among others, established through development in a multidisciplinary team right from the beginning, so several perspectives during the development, and safety through extensive empirical evaluation also from external partners that evaluated this tool and continuous monitoring. So I think these are just two interesting perspectives in this whole complex. Maybe just as a note, even this system still is just an alert system, which first a nurse has to control and then transfers to a doctor. So maybe the stakes are not as high as Cynthia Rudin says in this paper, but yeah, I think these are just two interesting viewpoints. Okay, so that was the first part. And now we're going to switch from an overview of the literature to work that I've done. And first we did a small jump in time also to kind of a little bit to the beginning of my PhD, where I set out with the goal to, I just want to give you some context here for the following two parts, to build and evaluate an interpretable machine learning system for routine healthcare, because at that time I thought there were too few instances where really transparent algorithms were evaluated for a clinical setting. And for my work, I a priori settled on these GAM models because I thought they had some compelling properties. First, they already showed that they have potential of being applied to healthcare data, as you remember in this entry example. They have this transparent model properties to allow a high level of safety and trust. We've seen in the Sepsis Watch example 2 slides before that there are, of course, other means to establish this, but I think it was out of the scope of this project to have this huge team of developing this and also having this high level of evaluation also with external parties and stuff like that. So that was really a huge project. And I thought in the smaller project it would be nice to go with a transparent model to ensure safety and trust. Also, I think they're relatively easy to understand also without a machine learning background. So this is quite nice. So the authors say they're just slightly more complex than logistic regression, which is nice because doctors know logistic regression very well. And I think it also feels much better if you can explain what's going on to the people who should use it in the end. And they're open source and have good technical support. Recently, Microsoft published a Python framework called Interpretable ML, where also these models are implemented, and it's hosted on GitHub, so it's freely available. And at the beginning, I was really open for a clinical test that was both relevant, had an objective label we could use for predictions. And then I found a cooperation partner, as I already mentioned, in the Department of Anesthesiology, and we settled with predicting 7-day ICU readmission. And this is just some very high-level flowchart I created for one of our first meetings, which is kind of the idea of this project, where it maybe could lead to this someday. So you have some data and you use it to train a model. So these are the graphs we've seen at the beginning already. And then the idea is that this trained model is presented to a team of doctors, which should check their clinical validity. And they should really ask themselves, should we make predictions for ICU admission based on these risk functions? And for instance, in this example, they would X out certain risk functions, say, okay, these don't seem safe for us, or there's like some wrong correlation that was picked up here, we don't want to include it. And then you would end up with a corrected model that you see this function is removed, that you would use for predictions. And you could also get some kind of explanations by just showing for a new patient where you are in these risk functions. And then in an iterative fashion, for instance, every month or so, you would use the newly obtained data to retrain the model and also use feedback. For instance, doctors would say, this function looks really fishy to us, so maybe we should remove it in the next iteration. And then you retrain the model, you get a new trained model, you again check the clinical validity and have an updated prediction model. So that's kind of the high-level idea that we had for this project. And this is also this was some very early results where I used data from 2018 to just set up a prototype, and these were some of the first risk functions that we've learned for blood sugar and creatinine predicting readmission. And I was actually happy because at least for the normal values for creatinine, that would be 0.8 to 1.2, so somewhere here. And for blood sugar, something around 100. You get at least lower risk than for other values. I mean, for blood sugar, you get even lower risk until 160, which is maybe not normal values anymore. But I was still quite happy with these first results. But in this meeting, I still remember really discussed, okay, what else is in these risk functions? So you could, for instance, see this fluctuating behavior over here, or with blood sugar here, this long tail to the right, where the risk goes down again for very high values. So that seems kind of confusing. So at that time, I had the question to evaluate whether clinicians can actually correctly understand and interpret these learned risk functions to determine if they can validate them for clinical usage. To just highlight this in this flowchart again, this is really the mission critical step. So if doctors actually don't understand the model correctly and don't feel safe to validate it, this step is kind of useless. So that's really important. And as you remember, as I said about evaluation of interpretability, we really wanted to evaluate that with doctors who should really use this tool in the end. So that was kind of some background and motivation for this side project, I would say, where we set out to evaluate the doctor interpretability of these tools. That's also the name of a paper that I presented at the Machine Learning and Healthcare Conference this year, which contains all the results of this work. And I just want to give you a brief overview about this. Our proceeding was as follows. We did an interpretability evaluation simulating the clinical validation of such a model. So that's exactly what we're interested in. That doctors got some risk function, had to decide, do I want to include this for my prediction or should I rather exclude it? And to this end, we used the standardized data set, Mimic3, also standardized tasks to have full reproducibility of our results, and included 12 doctors from different backgrounds. And then we developed the following questionnaire. And here in question 4, you can see the simulation, because here we really ask, would you include this risk function for in-hospital mortality prediction? Yes or no? So that's kind of the simulation. And apart from that, we have one part before this, we call it objective interpretability, where we ask doctors to answer questions, to read risk values from these functions, which seems kind of trivial, but the idea here was to familiarize them with these risk functions. And the second part here were statements. So we sat together in a multidisciplinary team, and for each of these risk functions, we really came up with some key properties that we wanted doctors to understand to really determine that they got like the gist of this risk function and really understood like the key points about it. And so for each risk function, we generated 3 to 5 of these statements that the doctors had to answer. And second part were so-called subjective interpretability, where we asked doctors about their certainty to correctly interpret a risk function and some qualitative feedback in form of text. If you now remind the slide where I have this taxonomy, I actually said for a very good interpretability evaluation, you should have a system without interpretability and with interpretability, and see if it really performs whatever you want to optimize. So in this case, we actually didn't do that because I think this was kind of out of scope. So we planned with 30 minutes with each doctor, and we also had this explanation video, which was also 10 minutes, already 10 minutes, and it was kind of outside the scope, presenting them a model without interpretability and with interpretability. So that's certainly a limitation. You could maybe argue that we are on this level here. The second one was a simpler task, which would be asking, answering statements about the model and see if people could understand it. So yeah, that's just some limitation of this work. Okay, so what are the results of this evaluation? We've seen that the ratio of correct answers for these yes/no statements about important graph properties was 83%. The median certainty was certain, and the inter-rater reliability for including risk functions for the prediction model was 0.01, so very low. And we got 96 written comments as feedback, of which 55 were negative and 41 were positive. We clustered these comments and sorted them according to their frequency. And here I just want to give you like the 4 most frequent negative comments, which I think are very interesting. So the first one was that the graphs show weak signals, which was confusing. So here you can see such a heat map, and you see large chunks of the function where nothing really is happening. So participants said it's very hard to make out like what's going on here. We're not sure why it's even included. The second one were complex function shapes. Of course, that's kind of a trade-off. If we use arbitrary function shapes, they can get very complex. We see an example over here where the function is like fluctuating a lot, which is hard to interpret. Then they mentioned varying bin sizes. Here you can see, so continuous variables are binned before this algorithm is applied. And over here you can see like a very large bin, and here there are very tiny bins, which are really difficult to spot. And participants commented on those. And also outlier values, it's something I've mentioned before. This is a risk function for pH, and with a pH of 9, I guess most doctors would say no one is living anymore. And so it is very confusing to interpret a risk function that includes a pH value of 9, because yeah, it doesn't make sense to you at all. Okay, so that was kind of the results from the qualitative feedback. And of course, in each machine learning paper, you have to have one of these performance tables. And the first two models are actually the baseline models that were provided in the paper that introduced the standardized task. So they ran a logistic regression model with 714 generated features and a multi-channel LSTM recurrent neural network. We trained a GAM model on all features to get a performance comparison. And you can see that surprisingly, actually, we perform just as good as this very complex neural network model. But keep in mind, it's really a lot of features, so you also get a lot of risk functions. But still, you could argue this is an example where this trade-off, again, doesn't hold really, because this model, I would still say, is more interpretable than this neural network model. And then for our evaluation, we said we have to reduce the number of features so that we have fewer risk functions that we have to consider. So we only used 34 features, which were the mean and the standard deviation of the last 48 hours of the collected variables, which gave us a performance a little bit lower than the logistic regression model trained on all features. Yeah, okay. So what are the main outcomes? We said that the evaluation suggests that doctors are able to correctly interpret such risk functions and also feel confident in doing so. Of course, this is only a hint because the study has several limitations, but I think there is a hint that doctors can interpret those functions. We've seen that interpretability depends on the complexity of risk functions. So we've seen that there are like certain risk functions where a lot of negative comments pop up. Also, we've seen that participants disagreed on which function should be excluded. This is this very low inter-rater reliability, which can actually cause a problem even if you have a very interpretable algorithm. In the end, you have to draw a line. So which functions would you really include or exclude? And this is, of course, not clear. I think the best proceeding there would be to have a team discussing these risk functions and deciding which one you want to include for your model, which ones you want to exclude. And I think one outcome is that really evaluations with human beings are very important to assess interpretability. I think it's the same as in usability. You think the system is working very well or it's very interpretable, but then if you really work with human beings, you see a lot of problems pop up and that you haven't thought about. Yeah, so the conclusion would be that GAMs are useful. So these models are very useful when there's little experience with machine learning. It's necessary to build trust. There are high safety demands and the data is not very complex. Yeah, so that were the results of this kind of side project. And now at the end, I want to give you some insights into work that is currently going on, where we use this model class for a 7-day intensive care unit readmission prediction. And the goal of this project, goals of this project are twofold. So the first one is to compare how does a transparent or interpretable machine learning algorithm perform compared to a validated clinical score and to other established machine learning algorithms. And secondly, what are consequences and problems of model validation? So what does actually happen if a team of doctors validates a model and removes some risk functions? Does that lead to a drop in performance? Or what kind of risk functions do we actually detect? Do we actually find risk functions that have a bias in them? Or maybe the whole model is actually fine. That would also be a finding. How do we want to proceed? We perform a retrospective study with data from 2001 to 2019 with ICU stays managed by the Department of Anesthesiology here in the University Hospital. And we consider stays that were discharged to a lower level of care, so intermediate care or general ward. And we use raw recordings from the ICU variables, which are quite a lot, over 6,000. So we need some form of automatic variable selection. As you already hear, that's something that we still have to implement. And yeah, then compared performance. So we use as a clinical score the SAPS2 score. We want to build a model based on the SAPS2 features because these kind of seem to be relevant. Otherwise, this wouldn't be a validated score. We want to compare this model with logistic regression and the recurrent neural network trained on the raw inputs. And so here there are not really a lot of results I can share. I just want to give you like an impression of the current state of this work. So this is kind of this flowchart you've seen before in a more detailed version. So you also see this arrow coming up here saying repeating this process. So this is the workflow for this project. We have the PMS system of the ICU. We have the hospital information system, which would be Orbis. We put all this data into a research database. And then we have two branches. The first one would be patient and admissions, for which we do ICU stays selection, which I'll show you on the next slide. And then for all this data that we have that we call recordings, we do some pre-processing and item selection and merging. So you have certain variables collected in several fields, and we put those into in a clean version that we call variables and values. And then based on the stays, we do label generation. So for each stay, we generate a yes or no label. So was readmitted within 7 days or not? And based on these variables and values, we generate features. Okay. And this graph is going on here with training, and also, so you see all this is done in Python. But at the bottom, there's actually visualization and validation of this model. And for this, we can actually reuse a tool we've developed for our evaluation, which is implemented in Java. So we export these models and load them into this Java tool to display these risk functions. And then people or doctors could inspect this model and really validate those models, and also say which risk functions they want to exclude. So as I said, I briefly want to share some info about the state selection. So in the beginning, I was actually quite happy with this objective label of ICU readmission, which is kind of a hard endpoint. So it's often important in machine learning that you can rely on like a really clear label. So I thought that was really good to work with, but still there are some difficulties. Just to show you some. For instance, you have to exclude cases that are discharged to other locations because you don't really know what happens to them. They might still be in intensive care or no care, or even discharge them home, but at least you don't have data of them anymore, so you have to exclude those. You also have to exclude cases discharged to excluded ICUs, so we don't include all ICUs of the university hospital, and these patients are still in intensive care, but we don't have data of them anymore, so we have to exclude them. On the other hand, you have to include cases that are discharged and then readmitted to an excluded ICU because they go from intermediate care, maybe again into intensive care. Even though they don't come back to one of our ICUs, they still go back into intensive care. So you see there are a lot of details you have to keep in mind. So it's a little bit more complicated than I expected in the beginning. Also, you have some problems in the data. Usually there shouldn't be breaks between stays and Orbis data, but sometimes there are breaks, and then you have to detect, is it due to intervention or maybe surgery, or is it rather, or is it really a discharge? Because if it's a discharge, this person coming back would receive a positive label. If it's an intervention, we don't want to label this stay as positive. And even after you do all these exclusion-inclusion criteria and merging of cases that hopefully belong together, you still have, like in this case, 200 cases which don't have a heart frequency recording, which everybody should have in the intensive care unit. So yeah, you see, you will always end up with some problems here, and maybe the main takeaway here is that real-world healthcare data is often messy. I guess most of you know that already. Just want to show you that it happens over and over again. And this is just an overview of my configuration of my pre-processing. As I told you, it's over 6,000 variables, so it's very tough to get an overview about that. I started out with a JSON configuration, which started to get very confusing. And now, please don't laugh about me, I really use an Excel sheet as a configuration because it has this nice property that everyone knows Excel, and you can actually share it with your partners. So I could also send it to my doctors and ask them some questions about pre-processing steps that I put into my configuration file. I also have a question column where I can put in some questions that I have, and also notes column, which helps me to keep track of information I have about certain items. And just to give you an example, here we see heart frequency. I generated some statistics to get an overview of these recordings. Then I can make a decision. Here I say included. I say where I can find the data. I can apply pre-processing methods like lowercase all values or filter certain values. A variable name where this value should end up in, type, value range, unit, and some post-processing procedures. And so this is all for variable generation. So I get a clean version of this recording. And then for feature generation, I put it into a category called time series long in this case, saying it's a time series feature. So, which I want to watch over a longer period of time. So maybe the mean, standard deviation, max, min over, I don't know, 7 days or something I generated. So they have certain methods associated with this feature class. And there are some more complicated variables like blood pressure. You can see it up here. These three are blood pressures, but also down here. There my decision is merged. I have several columns where the data lays, but they all end up in the same variables. And for these merged variables, I implemented like custom merging procedures for blood pressure. That's important because it depends on where you measure blood pressure. You have to apply some kind of offsets. So it depends on the location. And depending on this, I correct the blood pressure recordings before putting them into a variable. Okay, so that just as an impression of my data pre-processing. And here I show you like some very preliminary results. You can see here two models. The first one, the orange one, is a model just based on the SEPS score. So it's like a single feature, it's just a score. And the second one is a GAN model trained on the features I needed to generate the SEPS score. And what you can see here is the receiver operating characteristic, which is very typical in medicine. So this dotted line would be random guessing. You see the model using the SEPS score is just slightly better, but it is a little bit better than random guessing. And a model using these features of the SEPS score does even perform better. So that's kind of a good sanity check that things are working. And on the other side, you see the recall precision characteristic, which I think, which just often gives you more useful information if you have an imbalance problem, as it is the case for us. But again, you see the results are like not outstanding or anything, but again, the model working with more features performs better here. And just performance-wise, so what would you expect? If you look into the literature for 7-day ICU readmission, you find a receiver operating characteristic of 0.66 to 0.81. And it's also, I think, intuitively it makes sense because predicting readmission to an ICU is quite a hard task because often you don't know, who comes back. So I think it's just a hard task you deal with, and I think you wouldn't aim for a 0.9 receiver operating characteristic here. But I still think that there is some room for improvement. Okay, just some words about the future. So there are a couple of experiments that we want to perform in this project. As I said already, this performance comparison. We want to do experiments for finding out the relevance of the number of risk functions, because this kind of affects interpretability. So if in the end we need 1,000 risk functions to get an acceptable performance, that would of course be a negative result. We want to analyze the effect of the number of bins, because we've seen in our interpretability evaluation that a lot of bins can really decrease the interpretability. So we want to see if maybe fewer bins are enough. And we want to analyze the outcome of model validation to a team of doctors that I've mentioned before. Some problems that we've stumbled upon already are when you generate features for time series variables, you have this min, max, standard deviation, mean, for instance. And min, max, and mean often end up in very similar values, leading to very similar risk function, which can be very confusing. I really hope that feature selection helps us here. So it selects one of these, min, max, or mean, and then the other ones get really irrelevant and are hopefully deleted. So yeah, that's one problem. And another one is how to treat unknown values. Right now we do it as distinct values, which are treated separately. And I'm not sure if that's the best procedure, but yeah, that's our current problems. And that was everything I wanted to tell you about this project. And now we come to my last slide, trying to conclude everything that I think was relevant in this talk. So if you remember the first part, I tried to show you that machine learning has some inherent problems that we should keep in mind and should be aware of. And interpretability is one tool that might be able to reveal those and maybe could help us to get rid of them. It's certainly not the only one. Probably, I'm not sure it's the best one. It's just one possibility to approach these problems. I try to convey to you that interpretability is highly context specific, so you should always ask interpretable for whom, for which task, to which ends. And then you should, and it should be evaluated with real human beings. There are two classes of methods you could use. First one, transparent models, where you can really understand the whole model, and Postdoc explanations, which try to give you some impression of the inner working of a very complex model, but they can't cover like the whole inner working. That's very important to keep in mind. And the need for interpretability certainly depends on the application you want to use it for. For the second part, my takeaways would be that GAMS seems to be a useful transparent model class that can be applied in the healthcare domain. And again, really that user studies really reveal the complexity of certain problems, similarly to usability studies in interpretability. And then I would just want to finish with a funny XKCD comic that you can all read for yourself now. Yeah, and I think this is sometimes how machine learning can be perceived from an outside perspective, or maybe from statisticians. And maybe interpretability can be one tool to shed some light on this crazy pile of math that is going on there and make machine learning methods more safe and more reliable than it's illustrated in this cartoon. Okay, thank you very much.
Thanks very much, Stefan, for this great talk about the interpretable machine learning. So you can see a lot of virtual applause here.
Thank you very much.
A lot of very, very interesting insights. So I propose to do the discussion. Maybe we are now here 16 participants, so I think we can directly ask. So if you want to ask a question to Stefan, maybe just switch on your camera and go ahead. Okay, if no one dares to ask the first question, I might start. I think one key issue when working with clinical data is data quality in terms of completeness and plausible values. So what is your opinion or your preliminary experience regarding data quality in this field? So about what would be minimum requirements regarding data quality, or what filtering approaches do you intend to follow to prepare the data for your AI analysis?
Yeah, that's a tough one, of course, and we discussed about this topic already. So one thing I would clearly say is that these transparent models help you to keep track of your data quality because they make it more visible to you. With these black box models, for instance, with neural networks, I mean, it's kind of appealing. You just take your raw data and put it in, and you often read, yeah, you get very good results by that. By these, for instance, the models that we apply, you always see, as I've shown you, these risk functions. So you see exactly which data you have to make predictions on. And then doctors come and say, where does the blood sugar of 600 come from? It doesn't make sense. And you really, so I think that's something, on the one hand, positive, because you see mistakes in the data, but it also means more work, because you have to do much more extensive data filtering and preparation. And to which level this is necessary, I don't know. I think for interpretability, because humans have to make sense of it, you need certainly a higher level of data quality, which means more work for data cleaning, which is, I think, like the largest amount of work that you have to put into this work. But yeah, there's probably not a clear answer to this. I think we discussed that, and like an iterative approach could be very useful here. this is also why I trained this model with the subs features, which should be kind of a start. And then from there on, we need some kind of automatic approach because there are so many variables. From there on, we could start adding features until like there's no really a significant change in performance. I think that's really the best approach. Instead of doing extensive data cleaning of all variables, putting them all in, I think that's infeasible and not practical.
Okay. Any further questions, comments from the audience? Don't be shy. Now you have the expert here and you can ask a question. So when I hear this presentation, I remember to one of my teachers who explained me this curse of dimensionality. So when you have so many features, and then you would need many different individuals, and so the number of patients we have is high. So it's really high when you look at your ICU data set, but from a medical perspective it's high, but from a data perspective sometimes one would like to have maybe millions of patients, which is not feasible. So from your preliminary work, I think you are optimistic that you can derive some clinically meaningful conclusions from this data, correct?
Slightly optimistic, I would say. I mean, in the end, yeah, I think even if you can show that you won't reach extremely good performance, that would also be some kind of result. But yeah, I still think we could develop like a useful model from this. Yeah, I really think that. And maybe about your first comment, I think in machine learning, you really often stumble about these basic problems that we all know about, this curse of the dimensionality, for example. For instance, in the beginning, like these wrong correlations that you pick up because you really work with routine data. So statisticians would, I don't know, go crazy about it because they really wouldn't work with this bias-free data. In the machine learning, we just take the data and say, oh yeah, it's really a huge amount of data. Let's do some model, building some models with it. So these are like really two different approaches. I guess we have to meet somewhere in the middle. The truth somewhere there is in the middle. But yeah, a lot of these problems that we stumble upon, I think, are already well known. Yeah.
Okay, so then thank you all for participating. Thanks, Stefan, for this really great and inspiring talk. And so thank you all. Have a nice day. Have a nice evening. Bye-bye. And let's give another round of applause to Stefan.